Hello. The second part of today's lecture is on RSA cryptography. So here we have two people. We have Bob and we have Alice. And Alice is holding a message P in her hand, and Bob wants Alice to send her this message P. And the way that Bob wants her to do this, well, Bob has to be a little bit careful because there is this person, Eve, who is the eavesdropper, who can hear everything that's being transmitted over this wire that Alice and Bob are using. And Alice and Bob know that Eve is there, so they take precautions. So what Bob does is he publishes two numbers, N and E, and tells Alice to send him the least positive residue C of P to the E mod N. Okay, so now this number N is a product of two primes P1 and P2. Okay, so Bob and Alice don't care if Eve sees all of E, N, and C. Right? So Alice sends C across this wire, and Eve intercepts it and reads it. And Eve has previously read the numbers E and N that Bob is telling Alice to use to encode her message. Right? So, all right. So Eve could find P from C if she knew the inverse of P modulo phi of N, right? Why? Well, if we have that inverse and it's D, then what can we do? Well, Eve can compute C to the D, which is P to the E to D, which is congruent to PED, which is congruent to P to some multiple of phi of N plus 1, which is congruent to 1 to the K times P, which is congruent to P mod N. Right? So if Eve knows little d, then she can figure out what P is. And that's what Bob and Alice don't want her to be able to do. Right? So now, if, of course, if Eve knew phi of n, she could find D by the Euclidean algorithm. Or by raising e to the phi of n, or e to the phi of n minus 1, I guess. So how could she find phi of n? Well, actually it's pretty hard to find phi of n if you only know n. And let's try to explain why. Okay, so we'll start with this lemma, which is phi of p1, p2 is p1 minus 1 times p2 minus 1 if p1 and p2 are prime. Right. So let's see. So we want to count the number of integers less than p1 times p2 that are relatively prime to p1, p2. P1, P2, well, that means they have to be relatively prime to both P1 and P2. So, so there are P1 minus 1 multiples of P2 that are less than P1, P2, and P2 minus 1 multiples of P1 that are less than P1, P2. So phi of P1, P2 is P1, P2 minus 1 minus P1 minus 1 plus P2 minus 1, which is P1, P2 minus P1 minus P2 plus 1, which is P1 minus 1 times P2 minus 1. All right. So if Eve knew phi of P1, P2, then she would know P1, P2. Of course, that's n, and she's listened in and figured and heard what that is. And well, she would know P1, P2 minus phi of P1, P2 plus 1, which is P1 plus P2. So she would know both the product of P1, P2 and the sum of P1 and P2. So she could solve for P1 and P2. All right. So this means that if Eve knows how to figure out phi of P1, P2, she can factor the product of P1 and P2. However, factoring is a notoriously difficult problem. Okay, so if she had a way to figure out what phi of the product of two primes is, then she could factor the product of two primes, and so that means it's probably very hard for her to find out what phi of the product of the two primes is. Right? So let's look at an example. So suppose n equals 713. Okay, and okay, so if Eve knows phi of 713, which is 660, okay, So 713 is actually the product of two primes. I'm not telling you which primes they are, but I'm telling you that their phi of their product is 660. So then Eve knows these two things. P1, P2 is 713, and P1, P2 is 713. That's n minus phi of n, phi of 713 plus 1, and phi of 713 is 660, so that's equal to 54. So P1 times 54 minus P1 equals 713, or P1 squared minus 54 P1 plus 713 equals 0. All right? And the quadratic formula tells us or factoring tells us what P is. Okay, so given that it's very hard to factor really, really large numbers, we can assume that it's also very hard to find phi of really, really big numbers, which means that it's hard for Eve to figure out what that inverse modulo phi of the product is. Okay, so let's look at an example. And here we go, example. So Bob tells Alice to send him p to the 7th modulo 713. So Alice doesn't know the factorization of 713. Okay. So Alice's message P is 211. Right? So Alice has to compute 211 to the 7, the least positive residue of 211 raised to the 7th power modulo 713. So she uses this repeated squaring method that we've been talking about, or that you saw examples of in Tuesday's lecture. So we first square it, and this is 44,521, which is congruent. Well, okay, let's just do arithmetic here. It's equal to 713 times 62 plus 315. So 211 squared is congruent to 315 mod 713. And 211 to the 4th is 300. Well, it's congruent to 315 squared, which is congruent to 99,225, which is equal to 713 times 139 plus 98. So 211 to the 4th is congruent to 98 modulo 713. So 211 to the 7th, which is 2 to the 4 plus 2 plus 1. So here we've worked out the binary representation of 7. This is congruent to 118 times 315 times 211. This is modulo 713. And to make a long story short, this is congruent to 583 mod 713. Okay. So